Okay, so to get a better handle on again who has dropped out and not, I am because the registrar sheet still shows 55 people, but obviously we have a lot fewer. So attendance sheet, that's probably the last time I'm going to do it, and will give me a sense of again who I have to kind of get removed from the class. So again, if you're present, put your name against initials against your name, and if your name is not here, add it to the end. Right now, there are 3 open spots in the class. I think there are 2 or 3 PhD students who will probably get the priority if they're in CES, CS or CES. Otherwise, CES MS students will get the priority, and then we'll go from there. So let's just make sure that you kind of, you might want to sort of circulate, make sure that the whole row gets covered. Okay. Okay. Any questions from last time? Anything about the hardware platforms? Anything else? Okay. Just a reminder that next Monday I'm not here, so I'll do a makeup by recording a class. But what you should meanwhile do is to familiarize yourself with Embed. I will be handing out a homework around it. So sort of if you have received your Embed by then, start playing with it, get it up and running, just write some toy programs or something. If you haven't, there's still a lot of online stuff that you can do, write code and all. You just will not be able to sort of run it, obviously.
You said that we can connect our embedded device with Android as a gateway.
You could, but you would, since we will have one homework where the embedded device and the gateway have to talk using GPIO. So if you are using Android, you will need to purchase something which lets you have some sort of a GPIO input to your phone. So such boards do exist because Google has often made noise about it, but I have never played with one. Usually these are little boards which hook up to the USB port on your phone, and then some software on the phone kind of lets you do it. It's not something I would recommend, but you should be able to do it that way also.
And for the project, can we use embedded device paired with iOS device talking over Bluetooth or?
Unfortunately, not. And the reason is, okay, yes, you could. So the deal is the following: that Apple requires anyone who is interfacing with that connector to be a licensee. So what that means is that there are no open source type, whatever, cheap hardware floating around. I have seen a couple of companies who market special boards and cables which work with iOS devices in that way, and they get the appropriate license chip. Actually, that connector on iOS devices actually requires a special Apple provided chip on the other end. Okay, so if you have one of those things, I mean, I think I had purchased one long ago and played with it and all, but they're hard to find.
And my question was, can we talk via Bluetooth?
Yeah, for the Bluetooth LE part, certainly you can. For Bluetooth serial, you cannot. But we will be using Bluetooth LE, so that part is fine. GPIO, you won't be able to. There isn't a cheap or well-known way of doing it. But if you jailbreak your iOS device, then you can. Okay. You'll still need some hardware around it, but then you can buy stuff to cut that. Yeah. Any other question? Okay. So just to sort of recap the last few slides I was covering towards the end of this. So one common view of looking at these IoT embedded systems that are out there is really in terms of these 3 tiers, if you may. Kind of the device, or some people call it the embedded tier. I like to call it device just because there's wearable and implantable and these kind of things also. There is this gateway kind of a tier, and then there's a cloud. Almost any interesting stuff that you see out there now really has these 3 pieces. Sometimes this middle piece is not there because the embedded stuff itself may have a cellular radio or things like that to directly talk to the cloud, but this is a pretty sort of a generic model. And there are a whole bunch of technologies which have kind of emerged at this stage to cater to this kind of a model. Processors, which are really optimized for low power. They tend to have very little resources and all platforms around it, and so on and so forth. One thing over time, a way to deal with complexity, whether it be hardware or software in recent years, has been that you begin to deal with what are called as platforms. So there used to be a time you would work at the level of electronic components, create stuff and all, but that has a higher barrier to entry. So what has begun to happen is that oftentimes a well-defined collection of components gets created by someone, catches on, that becomes the platform of choice. So things like Arduino, Mbed, they really are that. I mean, they're a suite of software. In case of Mbed, for example, a bunch of libraries, an Mbed operating system, if you may. And then there are specifications that the hardware has to meet, and then a whole bunch of vendors create hardware corresponding to that specification. So in case of Mbed, for example, it requires that the board be capable of talking with your host, laptop, PC, whatnot, in a particular way. There's a special interface that has been defined, and any vendor can kind of do it. So if you go to the Mbed website, you'll see there are probably around 50 or so different boards at all price points which do that. So they are all complying with the platform specification, and therefore they can run that software, but within that there's a lot of differentiation. Whole bunch of technologies for both physical level communication of data as well as stuff on top of it, kind of the higher level protocols, if you may. These are usually optimized for very low rate, short distance kind of transport, as well as sort of dealing with issues. So if you look at some of these things, they kind of deal with things like how do you discover devices. One of the big challenge when it comes to this embedded space is that we are dealing with a large number of devices. So there's a lot of work going around things like making the network configuration relatively easy. So being able to discover who is out there on the network easily, manage their addresses, those kind of things. So a lot of these higher layer standards kind of deal with those kind of issues. They standardize the way you talk to devices. So BACnet, like I mentioned, is something that is very common in enterprise type buildings, and also like buildings like these, sensors, actuators, all usually are BACnet. Middle gateway, we have kind of more sophisticated processors and operating systems and all. This is where you begin to essentially have something which is like our usual computers, but somewhat constrained with some dose of real time and kind of some embedded type stuff thrown in. And then again, kind of transport mechanisms, and then finally a lot of cloud services which have begun to emerge, catering to things which are more embedded in flavor. So for example, what I mean by that is you'll see there are services which are database services, and they are optimized for time series data, because a lot of stuff that we deal with is of that nature. Or there are, Zidely is an example of that. ThinkSpeak is an example of that. Other things they provide are things like processing time series data. So they might have like MATLAB type engines there, so that you can do signal processing on it, machine learning on that data, get events, issue actions based upon that event. So like ThinkSpeak, for example, based upon processing the sensor data stream, you can then come up with commands, and then you push it back all the way to the embedded device. So all these kind of things are beginning to happen. And at this stage, if you're a new application concept, at every layer there's a choices of platforms available, and you kind of compose these things. So you don't literally kind of go down to low level stuff. It's more like a plug and play exercise. And a consequence of that is that a lot of this work is being done by people who may not be necessarily hardware or operating system experts. They are not. These are application people who are now able to do it. So that's sort of a big change. Now the result, of course, is that it's great when it works. When it breaks, or if the performance doesn't work out, or security holes are there, and that is where kind of expertise becomes needed. So still, lot of long ways to go to kind of make things really idiot-proof in terms of kind of assembling things and all. A lot of research is focused on things like finding bugs, finding security holes, those kind of issues, which are still kind of relatively unresolved, or performance issues. It's very easy to design something. It's much, much harder to design something which is power efficient, meets the timing constraints, will not fail, all those kind of things that production scale system would need. I had mentioned that how gateway might seem redundant, but is usually a necessary evil because of the mismatch between the resources here and the resources there, and also the fact that communication tends to be pretty energy expensive. So the only way we need to know how to do power efficient communication is to do it over short ranges. And that's why we have all these specialized protocols out here, Bluetooth LE and wireless HART and all. And what that means is that usually this entity plays the role of kind of going from the short range communication medium to kind of longer range one. Instead of making every device big and power hungry, somewhere you have some sort of a more endowed device which kind of takes care of that. So gateway is something which will probably be with us because the dynamic range of technology is just way too much. On one hand, we can, in the cloud, we are doing things which are potentially operating on terabytes and petabytes of data and all, and are operating at multiple gigahertz and burning hundreds of watts. And on the other hand, we are dealing with stuff which has to be in microwatts and milliwatts, and just spanning that dynamic range in one go is just usually very hard. So this gateway becomes kind of an intermediate step. So many systems look like this. One thing which has been happening, and I think part of the reason that we begin to see a lot more products and all begin to emerge and all that, it used to be that when it came to the device side of things, it meant 8-bit processors and assembly language programming and things like that and all. And what has begun to happen in the past 4 or 5 years is that 32-bit type processors, so that now you have something more reasonable software-wise, have begun to emerge. And so there are processors which do provide pretty low power, certainly not comparable to 8-bit, but really very low power in absolute terms. And now you can create some pretty interesting products and all. The company which has probably made the most name in this space is ARM, which does not make the processors. It makes the design of the processors, and then a whole bunch of companies make those processors. So like the embed device that that I've asked you to buy, it uses the most power efficient version of ARM processor called M0 or rather M0 Plus. So that's their lowest end, but then you see kind of a whole hierarchy. So the M series, Cortex M series, which is kind of low power stuff. Then there is the A series, which is kind of what you find in your phones and all. So that's next up. And then finally, there is higher end of the A series, which they're actually trying to pitch in for servers and all. So there's kind of 3 distinct types of processor spaces which they are catering to. Now, having said that, there are obviously companies which have their own processors. One of the most power efficient processor actually is this TI has a series called MSP, which is found in many products and all. It's actually a 16-bit device, hand-tuned, very power efficient and all. So that's been one key enabler. Another key enabler is really, I'm sure you have heard this term, the maker culture, and many universities now have these so-called maker courses and all. And what that really means is that if you look at the different things that go into designing products like these or systems like these, now you can do it very easily. Without having a very sophisticated infrastructure out there. So literally we can fabricate things, most aspects of the things on our desktop, or at least just by shipping file and then getting the product back in a day or two, at small scale, cost effectively, and all. Big reason behind this has been the whole rise of manufacturing industry in China, which kind of caters to kind of all the manufacturers out there. So what they also do is they have sort of achieved efficiencies and all that they can do small volumes very efficiently. It used to be the case that when you're trying to make 1 or 2 of something, it used to be insanely expensive because you are bearing the entire tooling and overhead cost and all. But now what these companies do is they take designs of multiple people, bash them together, process it, and then amortize the cost, and they do so very rapidly. So it certainly sort of cost has lowered. In fact, nowadays, if you're creating a startup which is catering to this kind of a space, it's almost expected that before a VC will fund you, they will actually expect that you have prototyped and you have even managed to raise some money through the crowdsource funding model. So which is why on Kickstarter and all, you see kind of all these companies trying to get your money. A lot of them never succeed, but that's a way of kind of them prototyping something and kind of attracting some initial, essentially some initial customer feedback. So working prototype, which is fairly polished and all, and has all that elements kind of back-end service, front-end hardware and all. Hardware in many ways is now like software. I mean, when you design hardware, it's really essentially another point in the spectrum of like writing software. Literally, you can rapidly turn around, you can iterate, debug. It's not like I have to be very careful, and also multiple iterations. It's a good thing in a way, but it's many cases a bad thing also, because it's encouraging oftentimes very bad hardware design and all, and kind of things that people don't necessarily always understand, but overall on balance is probably a good thing. One thing which is still kind of missing is that as we are letting this technology, this hardware and software, to a level where non-experts create products, so these are people who are application people, they may not even be computer scientists, how can we have them design things which are still robust and secure and efficient and all? And I think that thing still needs to be done. Many universities, unfortunately not at UCLA, you will see the so-called design laboratories. Okay, Berkeley has it, Stanford has it, I know San Diego is creating one, a whole bunch of places has it. And typically what you'll find there are things like laser cutter. These laser cutters let you make kind of mechanical housing and kind of parts. 3D printers, kind of now 3D structures and all. PCB milling, you can actually literally in minutes fabricate a printed circuit board in your lab. The only difference is instead of being done chemically, they literally take a milling machine and kind of just etch away remove the metal. Okay, not as sophisticated as kind of making multi-layer boards and all, but very rapid sort of turnaround. So we are kind of at a stage that literally these are like other printers for you, and you just send a file and different pieces of your design, electronic and mechanical, are being built, and then you put them together, and voila, in an afternoon you have a prototype of your product. So that's pretty amazing, and pretty cool stuff which is happening. Now, if you need either something more sophisticated, or you happen to be a place where those kind of tools are still not there, then there are a whole bunch of companies catering to this. So like, for example, you can literally find sort of prepackaged modules which provide reasonably high-level functionality now. So like there are companies like SparkFun and Adafruit and all, they sell these so-called breakout boards, one of which actually I prescribed for the device side. They basically, what they do is they take these parts and all, the chips which are really meant for PCB designers, but then put them into form factors which become now self-contained, much more easily usable modules. So literally, you don't need to be an EE to use it. It's just kind of a functional black box. Then a lot of open source hardware. So we obviously hear a lot about open source software, but there are tons and tons of open source hardware around. And what I mean is design files which you can take and ship out and get things fabricated, modify it if you need, create your own chip. Is for roughly $400, you can get a chip fabricated from Taiwan in the stage. These are also called tiny chips. They are a few millimeters square, but that's a lot. It will not be the cutting edge technology, but that's still sufficient. There are FPGAs, which are programmable chips. So open hardware repository and opencourse.org, these are all websites catering to that. There is another one which I learned of recently called upverter.com, where actually entire board designs are present, including for BeagleBone Black. So if you want to create your own hardware, which is a slightly modified version of BeagleBone Black, you just fork it on Upverter, just like you would fork a piece of software on GitHub. And they have a editor and all there. You modify it there, regenerate the PCB, ship it to, let's say, Sunstone, and if you are willing to pay a fair bit of money, you can get it back a day or two later by FedEx. If you want to play it cheap, have a 3-week, 4-week turnaround time, you'll get the boards. There are other companies like China PCB1 and all, whose price points are even lower. So a lot of stuff out there. Konoko is a company which can literally manufacture, you send them 3D designs and they can manufacture things with all sort of material, including platinum and gold if you want. Okay, so it's not just like a traditional 3D printer. They can do all sort of cool stuff. So what has begun to happen is that if you want to pull together a reasonable embedded system with all these components, it's doable and people are doing it. Okay, so this is an example of a project, undergrad project out of UC Berkeley, where what this group did, senior level project in one semester, they created a smart cup. Okay, they designed the entire mechanical housing. Now, if you see the electronic parts, what they're doing is they took standard modules, combined them together into a custom configuration. So a lot of design at this stage boils down to finding things which are already out there as opposed to designing these things from scratch. And if something doesn't quite exist, a lot of these things are open source. You modify them and then send it for fab. And then, so in this particular case, I felt it was a pretty cool project. So they use some light color sensing and all to identify the type of fluid which is there. So whether it's wine or water or milk, and then they kind of give you at the end of it on an app on your phone how much of what you drank. Okay, and so it's not simply how much fluid you took, because some fluids are good, some are not. They actually seek to classify it based upon essentially a spectrometer, if you may, a very simple one, and then the volume they sense by some sort of level sensing and sort of combine it together. So these kind of projects are doable. They're doable in a few weeks time frame. In fact, I would encourage, if you have ideas like these, we have actually a lot of these pieces in there. And if you have something cool to do, I will provide the necessary funding to make it happen. My lab does already have a laser cutter, and actually I do have a 3D printer which is at my home, but it's probably much easier to get stuff fabbed through Ponoko. So there are options. So I would like you to kind of think more, think of a system not just as breadboards lying around, wires all over and all, because they miss the point. The beauty of embedded in variable is that they better be embedded in variable. That's when you get to work out all the intricacies and all. And so I like this kind of this particular example quite a bit, but there are several others on their sort of website like this. Okay, so that's an enabler. What else? So there are missing things also. There's a lot of work happening right now in terms of industrial, from the industry side and all, to let, how should these things talk to each other? So the problem is that everyone is making these devices and all, and they all pick up sort of different options, different APIs, different formats and stuff like that. So different devices at home or a building or not, they cannot even talk to each other meaningfully. So there's effort happening at standardizing some of this stuff. A small number of physical layers being supported, and then the way these devices talk to each other and all. One effort, so it's kind of like common language. One effort which has gained a lot of prominence is something called All Scene Alliance. Okay, so it kind of came out of Qualcomm for a while had something called All Join, which is essentially a protocol so that your phone could discover what are all the devices or whatever. Your phone or one device can discover what are the other devices on that network, what the capabilities of that devices are. So like, for example, a television can say, I can display images or video and audio. A speaker might advertise, I can play audio and these are my capabilities, the sample rate and whatnot. So objects or devices advertise their capabilities, and then you can discover them. So there's kind of a broadcast sort of querying kind of a protocol out there, and then you can pair with them and kind of send the data, and likewise for actuation and also like your thermostat can advertise, I know the temperature in this space, those kind of things. So All Join is kind of an open source thing and all, and All Scene kind of adopts that and kind of builds upon it. This is something that you can actually run on your platforms and all. They have Android client, iOS client, they have Raspberry Pi, these kind of things all out there. But as often happens, not everyone necessarily buys into an alliance. So there's some competing efforts also. At the same time, there's something called Industrial Internet Consortium, which is kind of in the same space, something called IPSO, Open Interconnect Consortium, and then finally IEEE, which is kind of our main standardization, which along with IETF on the software side, on the networking side, tends to play the dominant role in defining these standards. So these guys are also have initiatives going on. So a lot of stuff happening right now in sort of standardizing these things. Such efforts have happened previously also, but since the technology wasn't as widespread, they kind of remained limited into a single domain. So Can someone give me examples of standards that you might be aware of which were targeting objects or things discovering each other and talking to each other on your network? Anyone heard of like UPnP? Every window, yeah, go ahead. Yeah, universal plug and play. So what does that do? Right. It basically lets you discover things. You never need to install drivers and all. You plug stuff in your network and all. And if you are operating within the Microsoft Windows framework, then things just discover each other. Your PC discovers the TV discovers the fact that you have videos on your computer, your stereo system can discover each other and all. Apple similarly has something called Bonjour. So if you're within the Apple framework, actually, if you use Macs, if you just go to your Safari browser and you usually see a tab called Bonjour, and you would see that as you have printers and other kind of network gateways and all on your network, they all automatically kind of appear. They get assigned a name, their capabilities are exposed and stuff like that. So there have been these kind of efforts floating around. There were in some years ago, Sony had pushed for something called Havi, which was for home audio video. That didn't go much where. In 90s, Sun had something built on top of Java, and so on and so forth. UPnP and Bonjour are quite common right now, which is why now like hooking up with printers and all is actually relatively straightforward. You plug them in and it works. Scanners, these sort of things. So same thing happening in the IoT space. No, there's not much of a self-discovery there. You have to, I mean, what's happening there, I guess, okay, some level maybe, okay, I mean, it's not so much doing the kind of discovery where I'm broadcasting and discovering what is out there. In that case, you have registered, and because you have an account, you kind of know, so not quite. And they cannot do this kind of stuff because then they would be flooding the whole network, whole internet, so it's not kind of viable. Okay. So if you look at the device tier, I've gone over these points before, but generally these tend to be more resource constrained and therefore more specialized devices. One way we know how to make things more efficient is to make them less programmable. Okay, the more general purpose in functionality something is, you're going to pay for it in power and performance. So usually at the leftmost tier in our diagram, you would see that there is a lot more application-specific type hardware and software that exists. Nevertheless, some degree of programmability is almost critical now because we don't know how to make things which are bug-free in the first go, okay, because they're just too complex. So some degree of programmability after deployment becomes important. Even perhaps changing the hardware functionality, which can be done also if you're using appropriate type of hardware. One other thing you would see is that in these devices, there is a lot of concurrency. What I mean by that is, if you look at very early generation of 1960s, 70s type embedded systems and all, they would just do one thing, like poll the temperature or stuff like that. But now what happens is they're dealing with a lot of sensors, a lot of different things happening. So their design is very concurrent in the sense that there are a lot of things which are independent sort of taking place on the same hardware, usually a single processor, and they are still interacting in complicated ways. So the design of these things is tends to be a little bit more complicated, and we'll talk about it different ways in one of the later lectures. Increasingly, a lot of these things are also very high performance because they deal with sensors and audio, video, this kind of data, which tends to be very processing intensive also, and increasingly we try to do some intelligent stuff on it, machine learning type algorithms and all. The other thing that you would see in these devices is that they often are reactive in nature. That is, you would see the use of events quite a bit. So essentially there are two ways that we kind of interact with the physical world. One is that you are continually sampling something and you're just getting a stream of stuff in a periodic way, and that's how a lot of sensors at the lowest level operate. And the other way we operate with these things is that we push some intelligence down so that when something unusual happens, an event happens, then I receive it. So now my code or my system essentially is receiving events from various places, and depending upon what happens when that event comes, it does something. So some complicated state machine happening, and you may need to observe for multiple events, because at any given time the event may come from source 1 or source 2 or source n, and you have to be prepared for it. So you cannot simply focus all your attention on one event. So one way we know how to do this thing very well in general purpose computing is to have a lot of different processes which an operating system manages. One process is looking at user 1 or source 1, another at source 2, and so on and so forth. On low-end devices, you don't have the luxury usually of those kind of OSs and all. Oftentimes you're writing this code as kind of a single piece of code, and so you have to write these state machines and all which are capable of exhibiting this kind of concurrent behavior. So the programming gets a bit messier, and you often have to deal with issues of timing and things like that. Little errors which, so anecdotally, and so just in this class, I think it was last year or maybe the year before, I offered following homework, first homework, very simple, which is that you have to sample something, a sensor, every some time t. Okay, let's say t was every 10 seconds. Okay, so the typical model in this case is I sample, and then I arrange somehow using the timers and all in the processor to sample precisely 10 seconds later again. Very common mistake, which roughly 3/4 of the class made, was the following. A timer interrupt happened, they went, they sampled, read the data, and there was some processing to be done, and then they initialized the timer to fire again 10 seconds later. Okay, what's the mistake? Hmm? Oh yeah, time it takes processing time. So they're missing that. So what was happening was over time, it basically was just drifting away. Okay, and I was amazed that roughly 3/4 of the class made that mistake. Okay, because and these are the subtleties. And now an anecdotal like someone like this probably designed a very critical piece of defense equipment for U.S. military, which is back in the very first Iraq-Kuwait war. There was an incident where an incoming missile was not intercepted by the anti-missile system, and it had then landed in the base and killed a bunch of soldiers and all. And the problem there was that so time is used there to identify how fast the incoming missile was traveling and then intercept it. Okay, now of course the time is being maintained by whatever this computer was running, and except that it had a problem equivalent to this, which is when its clock was slowly moving away. Okay, so the longer the system had been operating, the bigger the time error was. So they were usually that system used to crash quite a bit, so they would reboot it, so the error would never build up that much. But this time around, apparently the system had been up and running for more than a month, so there was significant error. So the incoming missile, the time, tried to predict where the missile is going to be, shot the interceptor, except that it was headed for the wrong place because the notion of time was wrong. So timing errors matter a lot, and stupid mistakes really can kind of kick in, and they're very hard to detect. Okay, because our programming languages are not designed to let you express time at all. Okay, I mean, we all program, and I don't think you can identify, other than some hardware design languages, we don't even express a notion of timing constraints and all in our languages. Okay, so we just don't know how to do that very well.
So in the example you provided, how can we figure out what was the processing time? It's just, you have to iterate.
Okay, so I will not tell the answer. Can someone tell me how would you do it? Okay, so that's one approach. That's one approach. Okay, but I would submit you don't even need to know the recording time, processing time, as long as we make the reasonable assumption that the processing time is less than the time period.
Then schedule the new timer just as the new data arrives.
Exactly. So you do it before you start processing. Okay, so that will do the trick. So you have to think about these things. Now, of course, the assumption we are making is that processing time is less than the time, and that usually you can test for and all. Okay, so very important to get these kind of subtleties right. This reasoning about time is unfortunately something that is very easy to make mistakes with. There are support that OSs have begun to provide for this. So for example, in some software environments, you would see that they will give you some API where you can attach a callback to a timer. So instead of writing code the way these students were doing, in embed and all, you can write code in a way where you can say, I have a timer, and whenever this interrupt comes, call this function. So now you have suddenly decoupled thing. There's someone responsible for generating an event every 10 seconds or whatever it was, and then your function is just doing the necessary work out there. And that would have avoided that problem also. So there are support that a lot of OSs provide to kind of even begin to prevent these things. The harder part is once you have made that mistake, we really don't have tools to let you discover those mistakes other than when things don't work. And these were tiny little errors which just build up over time. And what was happening in this case is that stuff was running, we were grading, and the way we were testing was that the signal being output by the homework hardware system, we were checking it against a reference signal on an oscilloscope, and then immediately you would see that they were not matched, and the scope will not fit. Okay, so that's an example.
So the processing time took longer than 10 seconds, right?
No. In those examples, the problem was not that processing time was taking longer than 10 seconds. The problem was processing time was much less than 10 seconds, or much less than whatever the time was. The problem was that they were starting the timer after the processing. So what was happening was, so this is what's happening. If I were to write it out here, what I want to do is every some time t, I want to do some processing. Okay, and you're programming it at a low level. So so at your disposal, you have some sort of a command saying, wake me up, whatever, wake up in some time delta. Okay. So the idea, so what was happening was what these guys were doing was they were calling out here this function, wake up in t, but they are not accounting for this time x which has been consumed. So now what's happening is wake up in t would happen, and so their execution was looking like the next execution would happen out here, and this time was turning out to be t. Okay, so that's so their period was really t plus x. Moreover, x tends to be jittery, so even the waveforms were not stable. Okay, so it's an example of kind of a type of timing mistakes and all. It's very easy to make at the lower level. Okay, and there's a lot of other stuff goes on, right? I mean, we were talking about could we measure this thing? So I think you gave the suggestion. I can measure out here and I can measure out here and compensate for it. The problem with that is, what if something else is running on the processor? What if an interrupt handler came and used some of the time in the middle? So your measure of x is not precise anymore. Okay, so what your strategy you were saying would work only if that's all I'm doing on the processor, but in reality that's not the case. So other stuff goes on that you don't really have control over. You cannot disable the interrupts and so on so forth. So programming at this lower level kind of requires a mindset which is different than kind of our usual read a file, process the data, output a result kind of thing. Okay, and time plays a very critical kind of role out there. Okay, another, let's see, so what were the points I wanted to cover out here? So time matters quite a bit in this kind of interaction. Sometimes things are periodic, but a lot of times things are aperiodic. That is, they could come at any time, and you better be prepared to handle them and respond to them. And oftentimes you have to respond to them within a certain bounded latency. And so quite different than what would normally call as transformational programming, which is simply take an input, compute something over it, output the result, and you're interacting with a human being who has a lot of tolerance to that. Interaction with environment causes problems because the environment tends to obey the laws of physics. Okay, so it's inflexible. Okay, whereas on the other hand, our computation and all can have all these indeterminacies, like effects of interrupts, or even other things like, let's say I write a program, it's processing some stuff, but the processor has a cache. Now the time x out here would depend upon whether when you started running, the data was already in the processor cache or not, because if it was not, it has to fetch it from the main memory, it will take some more cycles. So things which often help with performance in general purpose computing can result in causing indeterminacy in crucial parameters of your system when employed in these settings. And then it all depends upon whether it's tolerable or not. I mean, if I'm looking at an indeterminacy of a few microseconds in an hour type system, doesn't matter. But when you are operating with smaller time scales, it can make a big difference. So physical environment is intolerant. On the other hand, our computing substrates are highly variable in this regard. Okay, there are a lot of indeterminacies. So handling timing constraints is kind of a number one, first class kind of constraint that you have to deal with. You cannot kind of just brush it away. So when you write these things and all, you have to deal with. This is what kind of people who write device drivers and all in general purpose OSs also have to worry about, because they are the one who are working close to physical devices in the physical world. We are shielded away from it when we write our normal programs. Real time is not about being fast. It's actually about meeting the timing constraints. Okay, so usually predictability is more important than just being fast. In fact, in many cases, you can easily come up with situations where you throw a faster hardware and things will break, whereas the slower hardware, they were working fine. So fast doesn't necessarily mean good or better. Okay, a faster hardware. So that's an issue also. And then predictability. So when we talk about performance of, let's say, interactive computing and all, we usually focus on average performance, throughput, those kind of things. In the embedded world, or closer you are to the hardware, it's the predictability which becomes kind of more important, and that's something that you have to focus on. So worst case performance is something that you have to care about, not just average case. Okay. Looking at a typical platform, what you would see at kind of the bottommost tier of a system, you kind of have things that, some of the things that our usual computers have, but then other stuff also. So, yep, there is going to be some sort of processing entity. Could be a CPU, could be some dedicated piece of logic, some custom data path or something. There will be sensors, because we are interacting with the physical world, and there will be actuators, which, because again we are interacting, okay, or at least one or the other. If it's not, then it's not really playing any role. Usually you will have both in some form. So actuators refer to things like motors and artificial muscles and whatever, various kind of things, which in some way can affect the physical state of the world, generate sound, produce laser beams, stuff like that. And sensors, obviously, we know what they are, kind of different ways of sort of sensing the state of the physical world. You'll have some sort of a power source. Usually at that tier, we are looking at things where we don't have the luxury of being plugged in. Sometimes you may, but most of the time you don't. And therefore, you're usually operating off either some sort of a battery or some sort of an energy harvester, like a solar panel, or energy from vibration or stuff like that, or sometimes both. You will harvest energy and then store them in the battery for later use. So like a solar panel may harvest energy during daytime and store it into a battery so that at night time you can continue operating. You will have some sort of a communication link. Again, wires are usually not a good option at that tier, so you will see wireless and BTLE or BLE, which we are using in our hardware suite, is an example of one of the more recent technologies, but there's a bunch of stuff out there, and they'll keep getting more and more stuff. Like, for example, kind of radios you would need to talk to implantable stuff and all is going to be yet another 10x lower power and data rates and all. So a lot of cool stuff which is happening. The nice thing is that increasingly you can get a lot of this stuff on a single chip. And I mean, when I started working in this area back in 90s, like literally kind of having a system like this meant having a big board. And now sensors and actuators aside, in many cases those also, you can certainly have a lot of this stuff on the same chip. Even batteries on the chip are possible now. There are these thin film batteries which have begun to emerge, which basically sit on a corner of your chip, and there are specialized capacitors. The best example of something like this that I know is University of Michigan. They have one of the best groups in VLSI space. They have made a 1 millimeter cube device which has sensors, solar panel, battery, ARM processor, reasonable amount of memory. Okay, it looks really cute. I mean, literally 1 millimeter by 1 millimeter by 1 millimeter. It's a stack of 4 or 5 chips that they have made, and they bond one on top of each other, and that's what they have. You could imagine. I mean, I'm sure you have seen in some science fiction stuff or the other stuff going inside your body and stuff like that. You're not too far off from making that happen. I mean, this is stuff is pretty cool. Now, of course, solar panel won't work inside body, but some other harvesting stuff will. Let's see.
Maybe they can show it randomly and like the wireless sensor networks.
You know, yeah, so you're referring to these early vision.
Amounts.
Yeah, large amounts. So that will never happen because these things also cause other problems. Okay, but some approximation of that certainly could. Main thing is the smaller you can make these things, there are applications which become enabled, which are otherwise not possible, and that's really kind of the main thing. Okay, you can go inside physical systems and do things as opposed to just observing them from outside or changing their state from the outside. Okay. So I think there's a lot more to come, obviously, in this space because miniaturization we haven't seen anywhere close to what is possible. I mean, particularly with nanoscale stuff and all that people kind of begin to do. Okay. One of the crucial things that obviously at the heart of these things is the processing stuff. I wrote CPU out here, but really think of it as something which is processing information. Okay. There's a whole bunch of choices out there. It could be microprocessor type stuff. It could be specialized processors like signal processor or network processors or microcontrollers, which are basically things with a lot of interfaces. Application specific instruction processors. You can have processors whose instruction set you can optimize or change and then make your own stuff. So like maybe you do a lot of FFTs. So you can have a FFT some hardware for FFT and have that be an instruction. Reconfigurable system on chips. A system of chips where could be a little bit of hardware that you can program. FPGAs, gate arrays, these are all programmable type chips and then totally hardwired stuff. And basically what it boils down to is what speed, power, and cost structures you have. Higher up you are out here, your speed is going to be lower, needless to say, because if I'm out here, then I can specialize things a lot. So performance improves. Power increases, which means gets worse. If I go this way, that's another way of saying that again, more specialized I am, I can do things better. But cost tends to be kind of a funny thing. If I am creating just one of something, cost is going to be lower here because I'm sharing the design cost with a whole bunch of other users. But if I'm producing something which is in quantities of millions, then I'm better off out here because the savings in area and things like that I would benefit will swamp the thing. So basically, if you're in a prototyping business, you would be somewhere in the upper side of things. If you are in high volume market, then you would start going lower. Of course, if you're an Intel and all whose business is to cater to this side, you will stick out here. Now, having said that, the other issues also come up. Designing out here is more complicated. Okay, designing up here is easier because it's more software dominated. So these other considerations also sort of come into play. But oftentimes, it's the totality of a product, which is it small enough? Does it have a long enough battery life and all? These things are more important than simply the gigahertz and the MIPS and stuff like that. The totality of the user experience which matters. So where should that sweet spot be given your financial constraints and target market and all? This kind of complicated thing. The answer is not sort of usually very easy. One thing that comes up is, I mean, you can see that things are more software oriented, things are more hardware oriented on this side, and that often leads to this issue that any given functionality could be done in hardware, could be done in software. What should you pick? Sometimes it cannot be done in software because it would be too slow. Sometimes it cannot be done in hardware because it's insanely complicated to do in hardware. Okay, I mean, imagine taking some, I don't know, very complicated machine learning algorithm and say, hey, I'm going to design a gate level design for it. Good luck. I mean, you'll probably struggle for many, many years to make that happen. So sometimes these constraints just come in the way, but oftentimes you have a choice, and then you really get to kind of figure out where should you lie, and then that's where the cost, power, performance, all those things come in. Main thing really is that, I mean, one way of looking at thinking about it is, ultimately everything is hardware at the low level, and there is software at the high level. So software running on hardware. And what we call as a hardwired design or a software-based design really differ in how many distinct functionalities I'm running on a single piece of hardware. Okay, so it's the multiplexing of different functions on a single hardware. If I'm running a single function on a single hardware, that's a hardwired design. If I'm running multiple distinct things on the same hardware and therefore mediated by some sort of a scheduler, then I am more on the software end of things, and that scheduler is what one of the things that operating systems do. So it's really about multiplexing. Okay, a hardwired design is one software running on one hardware. That's normally what we call as a hardwired design, and kind of the other spectrum when we say software, it's really what we are saying is I have multiple pieces of software sharing the same hardware. Okay? And then there are intermediate sort of things which sort of fall into that. Okay. When you design hardware, it's not a whole lot different than software in a way, right? I mean, the only thing is that what elements am I willing to wait after the chip has been designed versus not. So let's take an example. Let's say I'm trying to design something which is going to just run a single state machine. Okay, I have several choices. I can get a processor and put that state machine as code on the flash memory on that processor on that chip. Or alternatively, I can design a chip where that code is residing in a ROM made at the time the chip was made. Or I can go even further and I can say, memory-based state machines are very inefficient. I'm going to create my own from my digital logic class, whatever I have learned, I'm going to create my own data path and hardwired state machine. All of these three things are doing the same thing. In fact, I'll reason about them the same way. I'll express my state machine the same way. It's just that what gets fabricated when. Okay, I mean, it's that. So compiling to a byte code for a virtual machine, compiling to instruction set of a processor, or compiling to gates on a chip. These are just back-end things. The front end basically is the same. So at this stage, whether you're a hardware designer, software designer, kind of you really, that distinction tools sort of largely make it transparent for us. So that was about performance, power, these kind of issues. The other set of challenges which have begun to emerge quite a bit now are things having to do with making these systems more robust. So this is an artifact of the thing that things are connected. So when we had standalone embedded systems, these were less of an issue. But now that we have systems that are getting hooked up, then they become an issue. I noticed that we are at 10:55 or so maybe we can take our 5-minute break at this stage because it's a logical break point, and then we continue. If you, I was circulating that sort of attendance sheet, so if you haven't signed it, make sure to do it. Otherwise, return it back to me, please. So 5 minutes. Yeah. Yeah, there are 3 openings, but and I'm pretty sure there are more. The class size is reduced. Yeah, so I'm going to wait for another day or so to think stabilize and then. And the other thing is I don't have PTE numbers. I have also defined. Yeah, there are open spots. My problem right now is that I don't have a PTE number to find out because there's no PTE number. But there were 3 spots, and anyway, looking at this, I think the
Professor Zara, I'm just kind of want to see the big picture throughout the course. So for now, these lectures are more explaining overall what embedded systems are, and so how is the course gonna go? I just
So we'll dive into these things like the software, scheduling, those kind of things, and we'll spend a lot of time on time synchronization and all.
Okay.
And then we'll go into security. So those are going to be three things. Energy, I do in a different course.
Which would be 202B.
202B.
Oh, okay.
Okay. Yeah.
Professor, it's like I have enrolled in a wait list last Wednesday, and I have stayed in around number 50. But it's
Where are you now?
There's really minor change.
Oh, okay. The
here.
waitlist number is not here, unfortunately. Okay.
And so
Yeah, but I see.
I'm also the CES track master student, and
First year, second year?
First year.
Yeah, first year I am not sure, but second years I'm pretty sure we'll should get it. Yeah.
So it's like my fellow students in the same lab. They are really way up in front, and they rank number 30 or 28. So they are really near.
Waitlist rank unfortunately doesn't translate into the same priority rank also. Okay, so just be careful on that. So I always go and consult Diana and then look at the status. So I have status for some of the students. The problem is some students joined the waitlist in more recent days. So unfortunately, I don't know whether they are first year, second year, what their areas are. Okay, so I'll probably.
So you mean you rank the first in the waitlist doesn't necessarily mean.
Absolutely, it doesn't necessarily mean that you will be the first one to get it.
Okay.
So you know the status of PhD students as well?
There were 3 or 4 PhD students.
Yeah, I emailed you last day. Regarding I'm a computer science PhD student.
Yeah, so if you're CS, so you were Mohammed. Yeah, you should get it. Yeah, because CS and CES PhD get the highest priority, and I have 3 slots, and so you would get in. My problem is a slightly different one right now. I don't have a PTE number to hand out. I need to get more from the university.
But I didn't fill out the form you sent.
Oh, that's fine.
That's fine.
Yeah.
So you know who PhD students are.
Yeah, I know who PhD students are. I know what the departments are. What I don't know is within EE. If you're an EE student, I don't know what your area is. That's where I kind of go to the department.
So how would you rate the chances of a master student first year CES getting?
Looking at it as of so, let's see how many enrolled did not sign up. I know there's one person who's out sick because he emailed to me, but so yeah, he was. I think it was Johan who was out sick. There is one enrolled student who did not show up. There are 2 who did not show up. There are 3 who have not shown up. So there are 3. Yeah, it doesn't matter where you are on this thing. So, okay, so there are 3 who have not shown up. Okay, so I'm hoping they dropped, and I know there are 3 open slots. So if I have 6 slots, you might.
For the IoT, let's say the embedded device, it can also have wireless access, Wi-Fi access, so it can directly report to a cloud.
It could, although it would be a more power-hungry device because of Wi-Fi. Yeah.
But that still counts as an IoT device.
Yeah, these are all. There is no hard thing really. In some cases, your power budget is fine. You can buy sensor-type devices which operate on Wi-Fi. Usually, they don't last too long on a battery, so they usually require to be plugged in.
So let's say for a project,
but that's
if
an
you
IoT.
want to design anything, that is still okay.
That's still okay too. Yeah. Yeah, so actually, you will, in the homework, you will deal with talking over serial port or I2C or SPI, sure. But the modules to do it are already part of embed and operating system, so you won't have to kind of do the low-level stuff. You should.
That's good. Because,
Yeah. Well, that's not good. You should learn how to do it.
Yeah, but it takes time. Yeah. Right?
Yeah.
So there's like lots of logic so to take.
Yeah, but these things are out there for every operating system, even at the low end stuff. If you go to embed.org and you'll see that for embed, all these things are out there. You don't have to write the stuff from scratch. Okay, so we can we can start. So one thing I just wanted to make sure that I'm not missing anyone. So there are a few enrolled students who have not signed out here. So I just want to make sure. Yan Liu, not here. Okay. Saswat Padhi, not here. Okay. Jinhua Wang, Jinhua Wang, not here. Timothy Wilson, not here. Lini Ria, not here. And Shiying Zhang, not here. Okay. So sounds like I have 7 or 8 names who didn't respond, and I know there were 3 open spots. It sounds like I may have around 10 open spots, which means those of you who signed up on the waiting list should have a pretty good chance. Okay, so let's go further. So security and kind of related to security is this issue of privacy. So let's take an example of kind of what one would think of as a large-scale type IoT type system which is out there, which is things which are being used or things which are emerging in the health domain. So what we increasingly have now is that sensors of various types, we either wear them or they could be in our environment. There are also stuff at home which kind of generally looks after activities and also older people and all. And all this data kind of goes into some sort of a system. At the back end, there are these electronic health record type systems which have begun to capture sensory data. There are sort of services like Runkeeper and all, which kind of are more fitness oriented, and then kind of Microsoft, Google, these guys all try to be in this business of kind of archiving and distributing data and all. And then eventually, kind of this stuff goes to caregivers, goes to you, and insurers and stuff like that. Okay, and there's a long history of this. I mean, this kind of stuff. In fact, I mean, for many years now, there have been these things like they're called Holter monitor, which is like people who have cardiac problems and also they are sent home with kind of a little, essentially an ECG unit with a little box that you wear and a smartphone that they give you, and then it continually kind of records your ECG, and if there is any cardiac event, it kind of goes up to a monitoring station, essentially monitoring your heart condition. Okay, and the difference now is that we are beginning to see these things penetrate into all sort of things which are even sort of for more chronic disease type treatment, general fitness and stuff like that. Okay, so in this setting, you can imagine a whole bunch of sort of attacks which are happening, can happen. We know how to do it, kind of situations and all. Tampering with the sensors, okay. Why might I do it? Okay, one is tampering with the sensor can result in some medically deleterious effect. Tampering with sensor can fool your insurance company. So there are all sort of motivations that different parties have. There are examples of 2-3 years ago, academic group out of University of Massachusetts and a couple of other places showed that almost every pacemaker which is currently implanted, it has a wireless interface which is used when you go to the when the patients go to the doctor's office, and then it's used to change the parameters of the pacemaker, like when should it trigger, with what voltage should it trigger, and stuff like that. Except that they are never designed with any sort of cryptography, any sort of a security control. Okay, so now that we can buy programmable radios, so-called software-defined radios, they showed that they can easily tap into it, and if they're sitting next to a patient with a pacemaker, they can essentially cause the patient to have some pretty bad things happen. Okay, so so these kind of things are, I mean, all doable and all. Okay, spoofing. Example of this I heard was, I was collaborating with some folks in India, and so there was an mHealth toolkit that they would send out, essentially kind of not social medical workers types in villages, and their job was to go around collecting sort of health parameters and stuff like that, and then kind of essentially it will then get shipped on the way to the back end, and then things like medical supplies and all were dependent upon that. Since there is an interesting black market in medicine out there, so there was a lot of spoofing going on. So what I mean by that is that the measurement has to be for patient A. Patient A is perfectly healthy. Patient B has diabetes, so you take his or her sample and then ship that, and now you have double the diabetic supplies. Half of it goes to the black market. so that kind of situation. So spoofing at the edge. Malware, spyware, very common, and viruses and stuff like that creeping into hospital systems and all are also there, and our phones are becoming kind of quasi-medical devices in some cases. That's what's happening there. Hacking at the back end, unauthorized access, unintended use, all these kind of things are things which we are used to in our pure software systems are there, except that their effect is far more calamitous in many cases because you're dealing with human life, physical system, whatnot. There. Some plenty of kind of interesting examples and all that have been pointed out or have emerged in recent years where attacks on the sensors and all have led to kind of some pretty dramatic things. So the vulnerabilities in the IoT system can reside in any one of those three layers. So the cloud component can be is vulnerable in many interesting ways. But the main thing out there is that our data, which is often very private or has consequences, is sitting out there in the cloud. And so it's a good target. It's a good target for hackers, and it's also a good target for governments. Okay, they can, under subpoena power or just spying, they could kind of do it. So like it could turn into blackmail opportunities and all. It could be insiders in the company which can do it and all. So the issue out here is the following, that the cloud services exist to process, store. If it was just about storage, things would be fine because we can just keep stuff encrypted and stored there, but that's not very interesting. So what's happening is a lot of these services seek to analyze the data, process it in real time, do something around it. The challenge which comes is, could they do those services without me sharing the raw data with them, without me sharing unencrypted raw data with them? And the answer is we really don't know how to do that very well yet in practice. So can we have an IoT cloud component which can do the kind of things we are talking about, not simply store, but processing, without seeing plain text sensor data? So take an example. So this is actually I've stolen from person at Stanford. So there's a notional application. The idea out here is that we want to identify automatically bad road segments. Okay, and the idea out here is whenever the car activates its traction control system, then it will send location, time, velocity to the National Highway Transport Security Agency, and it will thereby identify. And if it gets repeated reports in the same road segment, then we'll know something is happening and kind of action gets taken. The problem with this is that A, we have a government agency tracking the car. Secondly, there's some privacy implications and all, even relative to. So could we do things where the computation of what are the locations where there is a bad road segment can happen without an individual car being tracked? Okay, so could we design this kind of stuff where we could maintain the privacy and all, at the same time have a trustworthy thing? If we don't do anything, say anonymous stuff going out, well, a few problems out there. Firstly, this site cannot know whether it is a false report, who is it coming from, and all. Moreover, location and time can often, if there was some sort of anonymous ID associated, you can actually oftentimes track it down to an individual. So just imagine, for the sake of example, let's say my car were to send out anonymous reports of this nature to some server, and it does so, let's say, at some periodically or some time apart. Over the course of my days and months and all, it will get a whole bunch of samples, and if you begin to look at those patterns, it will probably lead to my home and workspace. You could easily begin to make out these patterns and all. So sensor data, when it is analyzed over periods of time, can begin to reveal identity, because once they find the location, it's not very hard to predict who the person is, because there are public records and all which are out there. So designing these things in a fashion which we would trust with our privacy and all is kind of a tricky one. So the notion out here is, could we design these things like that? So could we share encrypted data and still compute functions over it? And the short answer is, in theory, now we know how to do it. There are some very cool crypto techniques which have emerged in the past, literally 4 or 5 years, but they are still some orders of magnitude slower than doing this computation just over the plain data. But there's stuff happening. Gateway security, that's the other point of attack. So gateways are notoriously vulnerable. Okay, if you have Wi-Fi access point and all, most of them come with a standard password, which is usually open, and these are operating systems like Linux, where a lot of vulnerabilities have been discovered, but we don't patch them and all. There has been work going around which has shown that firmware for printers and gateways and these kind of devices are highly vulnerable, have a lot of problems and all. So attacks happen. To give you some example, there was one article I was reading where using the FOSCAM cameras, which is a very cheap IP camera, which are very popular because they are among the cheapest, made by a company in China. They had some significant vulnerabilities, and therefore there were episodes of hackers. A lot of people use them as baby monitors and all, so the hackers kind of going in there and then scaring the baby, because you could also kind of, it has a speaker, so you can kind of create sound and all. Okay, so this stuff was happening. So these devices that we deploy, hacking is not just something which will happen in theory, it is happening. Okay, and so again, protection against it. Another set of things is what kind of broadly I've just put it as sensors which are creepy and sensors which are vulnerable. So what I mean by that is, now we're not talking about stuff in the cloud or my gateway. I'm talking about actual sensors at the edges, and they have ramifications too. Yeah, there's some quote from a TV show. So a lot of stuff, sensors in our phone, things like smart meters and all, sensors in our bodies. The problem with all of these is that you could use them to make a whole bunch of different kind of information about oneself or one's spaces. And that, so I've just a list of kind of things that can be inferred from this kind of data, which often we just publish. In fact, there is very little sort of control over it as it goes on. Just to give you some kind of examples, smart meter data. So smart meter data, utilities capture at a few second granularity, and then they upload it every few tenths of seconds in many cases. This group at Germany showed that they could figure out what TV program or movie you were watching on your television from your smart meter data. So the concept out here is the following, that big screen TVs consume a lot of power. To make them more power efficient, what happens is that the backlighting in these displays, or if they're LEDs, then there's no backlighting, it's just LEDs, we turn off parts of the screen and all based upon the content. So if there are regions of black things, those are turned off. So a black screen would consume less power than an all white screen, and kind of different stuff in the middle would have different things. So what that means now is that the power trace of the TV, which is itself pretty big, a couple of 100 watts, let's say, is corresponding to the content on the screen. And this rides on top of everything else which is happening in your home, but it is there in the smart meter data with appropriate data mining ML algorithms. You can distill it out, and then you do have the luxury of knowing what is currently playing on the various cable TV channels. You movies and all have signatures. So now essentially you have the equivalent of Shazam. Anyone knows what Shazam is? Nope. The music app? Yeah, what does it do? You have it listen to an unknown piece of music and it tells you what it is, right? So it reduces the complicated song or whatever down to some kind of essence. Same kind of concept out here, except it's coming from power trace. Okay, so it's an example. Gyrophone. This is kind of pretty cool work out of Stanford. So gyroscopes on your phone. What do gyroscopes do? Angular velocity, exactly. And then in turn you use it for other things. Okay, so it's fundamentally measuring angular velocity. So on the phones, these sensors, they are done using MEMS chips. And in this particular case, basically there's a mechanical structure on the chip fabricated in silicon, which basically is a free floating mass which is affected by the angular velocity. When it moves, some electrical parameter changes, usually capacitance, which you kind of measure, and that's what you're sensing. So that's what's happening under the hood. Except that these guys kind of noticed, and the exact physics of it, they claim something may or may not be true, but the main point is that if there is loud enough sound in the vicinity, then that little MEMS object, which is measuring the angular velocity, vibrates. It picks up the sound waves. And therefore, you get a signature which corresponds to the acoustic spectrum. It's very undersampled. So those of you who are EE, it is below Nyquist sampling. So you cannot reconstruct what is happening, but you can do other kind of cruder identification. So like, for example, they showed they can identify the gender. They showed they can identify genders is pretty accurate, as you can see, particularly using support vector machine, which is a type of machine learning algorithm. They tried to identify speaker as an identity of the speaker, less so. They tried to identify some other things and all, and again, these things, they're well ahead of random guess kind of thing, but I mean, not perfect, but the thing is, combined with other information, they yield to some interesting ramifications. Other things, I mean, there's a list of kind of things that you can infer out there. If you look at your smart meter trace, you can actually tell what all you are running and all, okay? And in fact, there are some electric companies now, when they send you the bill, they tell you how much your fridge consumed and how much your oven consumed, even though you never told them what you have, because they have models of these appliances and they kind of analyze the thing. There's a company called O-Power, which works with the electric utilities, whose sole business is exactly that. Okay, so they can snoop on us. And moreover, if they can snoop, then wherever that data goes, they can also snoop around that. Okay, so potentially you could imagine kind of solutions being, maybe we might need some sort of a sensor firewall which can modify the sensor data as it before it hits the cloud, so that you can exercise some control over what is going to happen with that. Vulnerable sensors. So that's another interesting thing. Let me jump a little bit to show you kind of things that are happening already. So examples out here in nations all over, many nations out here, they're using sensors near traffic lights, which are not your usual magnetic loops, but these are little wireless sensors which just dig a hole into the road and is embedded. And these sensors are magnetic sensors, so when the car goes over it, they look at the signature, identify the car, the type of car, and stuff like that. And all. Comes out of a company at Berkeley, and they have been deployed over there. They have many holes in them. Okay, ranging from the fact that you could actually change their firmware over the air without requiring a password. You can snoop on them by a radio board that you can buy for a couple of $100. Okay, so what these guys have shown is that they can therefore hack the traffic light and then realize things like some of the Hollywood movie attacks and all, which they showed, like controlling traffic lights for nefarious purposes and all, so you could do that. Okay. GPS spoofing. Again, you can legally buy GPS spoofers. They pretend to be GPS satellites. You cannot use them legally, but nothing to prevent the bad guy from doing it. And then you can make things which are relying on GPS to have an incorrect notion of location or time, and whatever consequences follow from that. Other things, creative attacks. So students in a graduate class like this at Technion in Israel, a project they did was, they say Waze. So Waze, anyone knows what Waze is? Yeah. Okay, so it's a crowdsourced traffic. What these guys figured out was that, you know, we can create gazillions of fake Waze clients by running Android emulators, registering them, and then sending traffic reports about some road segment, and then essentially have fake traffic jams there. Or alternatively, if there is actually a jam, don't report it or whatever. Report a lot of clean things and all, and it cause things to happen. So there are a lot of these examples which are happening. So what they all boil down to the following, that attacks are no longer just on the cloud and all. They're actually happening right here. sensors and actuators. And then the effect, and this is where we least protect these things, and I mean that's the crucial, and they are the critical part of IoT. So understanding how to do these things, how to protect against these is kind of another challenge for IoT. I'm going to skip some of these slides. We're going to come back to it later. In smart grid context, so our electrical grids have these sensors called PMUs, phasor measurement units. These are basically very fancy current, voltage, frequency sensors. They're pretty costly, but they are in the electrical grid. And what happens is they synchronize the current, voltage, frequency using nanosecond accurate synchronized clocks. Okay, basically clocks which operate using GPS. And the idea is that if something bad happens in the grid any place, a branch falls, a wire is cut, a terrorist attack did something, some huge load comes into play and all this data is kind of immediately used to identify where the problem is and react to it. If I have a GPS spoofer, I can shift the sampling time by a few milliseconds. An AC cycle is 17 milliseconds in this country, so just within that. And then you can do things like make the fault appear to happen hundreds of kilometers away, okay, by judiciously attacking certain of these sensors. These are all attacks which are demonstrable now. So IoT systems will have to sort of come back with this kind of stuff as well. And so looking, I mean, this particular lecture was intended to kind of portray the broad landscape. So what we're spending the time on in this class would be, so obviously IoT has a lot of components. We cannot conceivably cover all of them. What I will cover are things like, so the next slide set, which I did not distribute, but it's on Piazza, will go into what is happening at the platform level, the hardware technology. Then we'll go into the software techniques that are used. We'll spend some time on scheduling as it is used with real time and all. Then we will move into kind of next year up. We'll spend a lot of time on time synchronization. So we'll focus quite a bit on timing issues. And then finally, security. The one big thing that I'm not touching upon in this class is energy. We'll have a little bit of that in the next lecture, but by and large not, because I have a whole 202B which focuses specifically on energy. It's a pretty big important topic by itself. So this course, if you're still shopping and trying to make up your mind, focuses on resources and timing and security. That's what we're going to sort of go after. And at the end of it, what my hope is that through sort of lectures and the various in-class material and all, you get a sense of and have hands-on kind of experience with, through projects and all, how to build this kind of a 3-tier IoT system which does something useful, get exposed to some of the technologies and all. So that's my kind of hope out of this course. Main thing to kind of reiterate again is that what we really have is these systems that they're basically sensing, extracting information, doing actions based upon that. And what you really have to do is to design these 3 tiers, kind of the embedded wearable side, this kind of gateway stuff in the middle, which could be a mobile device, for example, in the cloud. And all 3 of them you need to think about and kind of see how these pieces come together. The challenge here, if I were to kind of distill it down, is into kind of 4 things that one has to worry about the most. One is timing, that is performance. Second is energy, okay, these things at the edges are. Third is resilience. These things have to be resilient to kind of attacks and all. And the fourth one, which is very hard to pin down, complexity. These things are complex. There are just way too many moving parts, way too many protocols and different kind of hardware, software. And by the time you put them together, getting a sense of is everything working right? Where are the bottlenecks and all? It's pretty hard to kind of do it. And I think that only comes with experience. So that's what I kind of put it down out here. Okay, so in the remaining time today, which is another 20-25 minutes, I wanted to start from kind of the lowest tier, which is looking at some of the issues that occur at the platform level, kind of things that are happening and the processor and surrounding things, just to give you a sense of what goes there. This is the only slide where we will see some circuits in a few slides, okay, and that's it. So those of you who are CS students, just kind of peek ahead there. And then we'll kind of go into the software side of platform in the next lecture, and then move into scheduling and times. Okay, so if I look at a canonical embedded device, embedded system, so I had an earlier picture, I've just kind of expanded upon that. So some computing substrate, could be CPU, DSP, FPGA, ASIC, all those choices. It will probably have some memory. Memory itself could be pretty power hungry. In fact, one of the things I've often heard my collaborators and all at Qualcomm and all talk about is that actually memory, particularly static RAM, which is where kind of light data stores, is actually a huge bottleneck. Which is why what you would see is that amount of memories in these devices are still relatively tiny because it comes at a huge power penalty. Sensors, actuators, that's what makes them interface with the physical world. You would have some network interface, some sort of I/O interface. These are almost always there because you are interacting with something externally, unless you happen to have a purely standalone system. That's possible too. And then some sort of a human interface. Even the most deeply embedded of the devices tend to have something. Even like the pacemaker had the interface for the doctor because you need to kind of change it. And then finally, very crucially, you also have the power subsystem, where some sort of energy, way of getting energy, some way of storing energy, and some way of cleaning up the power so that the voltage and current you supply are adequate and time of the right nature. So these are kind of the main moving parts of a embedded device. And what I'm going to do is to dive into several of these. We'll spend the most time on this part, but I also want to give you a sense of what happens in some of these things, what kind of issues are
And
there.
also the processing will have it inside the like in the computation storage, or
well, you could offload stuff. You also have the option of sending the data out there, right? So the main thing is that yes, you could imagine systems where this thing is doing nothing other than capturing this data and sending it out and receiving command and sending it out. They're not very interesting. I think most stuff that you see begin to do some things out there. Even things like Fitbits and stuff like that, they are doing this thing. And part of the reason they often do processing out here is to reduce the amount of data you are sending out. Okay, because just to throw a number out at you, power, or rather energy needed to send one bit over a few meter distance tends to be anywhere from 100 to 1,000 times more than energy needed to execute one instruction. Okay, so another way of saying is, if I can save sending a bit, I have just bought myself a few hundred to a few thousand potential instructions. So the mismatch is huge. Now there are some technology changes which are happening and all, which kind of are affecting that equation a bit, but at least with traditional radios and all, that's kind of the number you have. So the reason we do processing is also to reduce communication.
But there's also a limit to how many instructions you can put inside the.
Well, the flash also tend to be, I mean, these things are all power and area hungry. So sure, you will have practically a limit. If you go and look at the page for embed devices, it's probably a fairly good representative. You probably see that most of the flash stuff is anywhere from 32 to 256 kilobytes. I think there are one or two platforms which are around a megabyte or so. That's pretty much the tops. Okay. SRAM, you would probably see anywhere from 8K to maybe, if you're lucky, 128K. Most of them are 16, 32K. Very tiny. Okay. So, short answer, you don't have a whole lot of room here. Okay. Again, there are newer technologies emerging. Flash is the workhorse technology, but there are newer things which are emerging in terms of memories which are persistent yet writable. So in the sense they can persistent in the sense they can store data across power outages, but yet writable, and they kind of occupy a sweet spot in the middle. So a lot of interesting stuff happening. They are still a little bit esoteric, so they haven't necessarily made into it. DRAMs or embedded DRAMs, so DRAMs which could be on the same chip as your processor, is something that IBM sort of pioneered, so to say, and made a lot of noise out of. So that kind of suddenly let you put higher amounts of memory in there, but then of course you have to refresh a DRAM, so it has its own implications. Okay, so it's a complicated value. Broader thing is you're probably looking at processors which are few tens or maybe 100 megahertz kind of speed, SRAMs or whatever, dynamic memories of some form, which are, let's say, a small number of tens of kilobytes, and flash memory, which are into small number of 100 kilobytes kind of thing. Okay, so that's the range that you are looking at. And usually devices like these, I mean, if you work in the reverse direction, these are size limited, Fitbits and all. They're probably operating on very tiny lithium batteries or coin cells and all. How much energy you have, you kind of work backwards. You want some reasonable lifetime for it to be usable. You don't end up with a whole lot of budget out there. In fact, probably the show-stopping thing about the smartwatch concept right now is that just the battery life, because we are seeking to pack stuff in them, but we are, I mean, just because of what we are willing to carry on our wrist, we are size limited. And I mean, Apple's iWatch is what, a day or two kind of life, and same thing with Samsung, and same thing with other ones. So I think we still haven't kind of worked out that miracle. Last time around, I had shown one of those various laws, Morse laws, Bell's laws, and Nielsen's laws. How much does battery improve? What do you think is the rate of annualized rate of improvement over the last few decades? It's pretty much as 1 or 2%. Okay, so basically, so the batteries, basically what happens is once in a while a new chemistry comes into play, right? So we had the good zinc carbon batteries, then alkaline, and then nickel metal hydride, and then lithium ion. If you look the past 60, 70 years, there are 4 chemistries. And then every time a chemistry comes, then initially the manufacturing is flaky, and then kind of things improve. So if you look at lithium ion, there are a lot of improvements which have happened since they became popular. But in what way? So do you think the energy capacity has gone up? No, that's the amount of material I have in it. So what ways have they improved? Okay, cost is one, sure. Lifetime, yeah. So lifetime, not in the sense of how long a charged battery will last. Lifetime in the sense of every time I recharge the battery, it ages. And so when do I need to replace the battery? So the number of cycles of charge recharge. So it used to be they were around 200-300. Nowadays they're around 1500 or so. So a battery which would last for a year now has a lifetime of maybe 3, 4, 5 years. And that's the thing which is changed.
I think from 2 quarters policies of UCLA invited a capacitor that you can solve your
Yeah. So carbon nanotube based or graphene based capacitor. So that's work with Professor Krainer's group here in chemistry. So they probably have some of the best technologies out there in that space. So essentially, you can trap stuff between. You can create very high capacity capacitors using graphene sheets. Graphene is this miracle material. Okay, and so where you were using rechargeable batteries, you can actually begin to use capacitors. There is a gap. So let's. I guess in the other course I talked a lot more about it, but basically, roughly speaking, batteries are good at storing lots of energy, but not supplying lots of power. Capacitors are good at supplying lots of power, but not storing as much energy. Okay, and the other thing is that capacitors leak. So when I charge it up, if I don't use the charge immediately, it drifts away. Batteries leak less. Okay, so which is why if you charge up a capacitor and visit it a week later, it's probably gone. Okay, now this is where some of the advances are happening there. With batteries, a recharge battery can last for a longer time. But again, these are both moving targets, and the work you mentioned is, yeah, I mean, it's probably the best out there right now in that space. Yeah. So a lot of stuff happening. Let's go into computation storage. So that's probably the most one of the most interesting pieces. So we talked about earlier that how there are many different ways computation can be implemented. If you're kind of designing your own platform and all, you could design your own custom chip. So I'm not going to cover that. That's only very few vendors can afford to do, like Apple, Samsung, and all. They certainly do that because they're looking at tens of millions of volume. In most cases, If you have a modestly high volume product, you're probably going to go after using some sort of an FPGA or some other system chip. It is quasi-programmable. You are going to buy cores, pre-designed thingies from other vendors, assemble them together. But even that is kind of rarer. In many cases, we just design using off-the-shelf stuff, processors that have been designed by others, and you just make a PC board. Even high-volume vendors like Apple and all do that also. So when the iPhone 5S came out last year, it had this so-called motion processor, which M7 as Apple called it. But M7 was really in disguise a chip from a company called NXPC. It's a ARM Cortex M3 chip, which was privately labeled for Apple. So even these high volume vendors, they often just use existing COTS parts with perhaps some minor customization. A lot of typical products you would see is that you basically create custom systems, boards, or even buying boards and assemble them together. Particularly at the higher end, once you look at bigger embedded systems, that's what begins to happen. And then also a lot of push towards using standardized platforms so that you begin to benefit from standard software environments that you can plug and play into. There are even chips where even analog stuff is there and it's programmable. There's a company called Cypress, and it makes these chips called PSoC, programmable system on chip. So they have processors, they have memory and stuff like that, but they also have configurable analog and digital blocks. So literally you can design a complete system, including the analog parts, onto this thing. So you have A to D converter, amplifier, stuff like that. Not the best. The performance, because they're sitting on the same chip as your digital stuff, so it's going to be not as high quality, but you literally can have a complete system. These kind of chips are very common in things like trackpads and mouse and these kind of things, okay, because just a single chip covers everything. Okay, most common for IoT type embedded systems, this tiny stuff being used in IoT is to use so-called microcontrollers. So microcontrollers is basically a CPU combined with ROM, RAM, peripherals all on the same chip. So that all you need to do potentially hook up to it is to connect with sensors, actuators, and stuff like that around that. So chip vendors usually pick this thing from ARM. That's a very common one. There are a couple of other providers of this, like MIPS processors are also pretty widely used by many vendors, but ARM is probably the king out there. So typical vendors selling microcontrollers nowadays, they will, in the 32-bit side of things, will take ARM. In sort of lower end version, there's some more varieties, and they put this stuff out there. It's a thing, and then you go to the catalog, you'll find all sort of combinations of different sizes of ROM, RAM, peripherals with different number of pins and all, which you can select from. Broadly speaking, there are three things out there: 8-bit market, 16-bit market, 32-bit market. Interesting stuff is really happening out here. These are pretty mature things at this stage, but these are very lower power. You can get into microwatt type regime out here, whereas here you are into a few milliwatt to tens of milliwatt. Some of the bigger players in this space, you would notice there's a company called Atmel up in Bay Area, whose processors, AVR processors, are very, very popular, and then TI's MSP series, which I had mentioned. There are two numbers which matter quite a bit out here. How much is the power consumption when the processor is doing nothing, as in sleeping? And usually that standby power is often a showstopper, particularly for things like sensors and all, because oftentimes that's all they're doing, like security sensors at home and things like that. Getting there into microamps or even fraction of a microamp is quite important. And the other one is how much power they consume while they are doing something, active processing. And that's where efficiency begins to matter. So it's not simply about how much power, but what do they do with that power, like how many instructions or whatever, how long your task will take on it. And a third parameter, which actually matters quite a bit, is how rapidly you can go to sleep to active or active to sleep. If you spend a lot of time out here, then going to sleep becomes very expensive, and then your system becomes very inefficient. So it's a combination of these things. So a lot of innovation in recent years really has happened in lowering this number and lowering this number. Okay, active processing type, that's traditional computer architecture, there's only so much you can do to sort of change that other than kind of, I mean, everyone uses some sort of a risk architecture, everyone is using sort of similar circuit design techniques and all. It's really these places where a lot of innovation and technology things come into play. So you'll find lots and lots of choices and combinations which are kind of out there. Next up, 32-bit space, you basically start getting into essentially ARM-based things by and large. They are, as I mentioned earlier, they are the common ones, and this is where you will begin to find things which are into maybe a couple of 100 megahertz, higher performance, but RAM and ROM are still kind of tends to be relatively modest, okay, because they tend to be power hungry. When it comes to peripherals, so actually these chips also have peripherals. So the kind of peripherals you will typically find are the following category. Lot of stuff to interface with some of the standardized interfaces which are very popular in sensing and actuation. So these are things like UART, SPI, Serial Peripheral Interface, I2C, which is a very old standard, CAN bus, which is what is used in our cars. So you'll find this kind of support. Then you'll find a rich set of timers and counters and things like that, because there's a lot of stuff that we do kind of is around that. And then final thing you'll find is A to D and D to A, ability to interact with the analog side of the world. So depending upon the marketplace they are catering to, you would see that these chips have different combinations of this kind of stuff happening. So low end, high end, and again, kind of thing that really, like I said, matters quite a bit is a differentiator often is the how low power it is. So unfortunately, I guess going back out here, making this thing very low typically means a higher degree of customization and a better technology, and that comes at a price. So TI's MSP processors are actually quite renowned for very low sleep power, but it's a hand-tuned processor, okay, literally like hand laid out and hand designed, and so a highly optimized piece of hardware. Not every company kind of does that. So the trade-off that comes at this level is that I mentioned, active mode energy efficiency versus power management, as in rapidity with which you can go to sleep or come out of it. So just to give you an example, this is these are a little bit old choices of processors, but nevertheless, since I have the data, they make the point. So what I'm comparing out here is a 32-bit embedded processor. It's an ARM processor, but around 10-year-old version. And then I'm comparing an 8-bit microcontroller. Okay. And what we have out here is data for execution energy, for FFT, CRC checksum, and FIR filter. Okay, so these are just three representative kind of functions that you will probably often find in these kind of things. Okay, CRC because you have to do error checking on data, FIR filter because you process sensor stuff and all, and FFT again, you process sensory stuff and all. What you would see, and this is a log plot, so you would see out here, right-hand plots are for the 32-bit processor, and the left-hand one is for the 8-bit one. If you just looked at the power, 8-bit is lower power. Its power consumption is lower, but it has an architectural disadvantage. It's operating on 8-bit data. It is operating, it has whatever, fewer type of architectural resources and all. So the net result is, you would see in every case, is orders of magnitude, couple of orders of magnitude kind of a difference between energy efficiency of the high-end processor versus a low-end processor. So message to take away from this thing is, even in the active mode, power and energy, these are two different metrics. Okay, if you care about power, peak power that you are doing, people end up using the 8-bit. But if you look at efficiency, the 32-bit stuff sort of ends up winning significantly. But the other point I want to make was sleep. What's happening when things are sleeping? Now, in this case, when this device, this processor is suspended, it is consuming power, which in this case is particularly bad, but even otherwise tends to be in milliwatts. Okay, whereas when the 8-bit stuff sleeps, it's in microwatts. So there is another 2 to 3 order of magnitude difference in the power consumption in the sleep mode. Now, when it comes to sleep, all you care about is power. Energy doesn't matter because we are not doing anything, right? I mean, so whether there is no definition of energy out there, it's really all about power. That if I'm asleep for a certain amount of time, what is the power consumption doing, what's the average power consumption during that time. So that's one metric. The other metric is how much time it takes to wake up and all. And in this particular case, so this is an ARM processor running Linux, and it takes around 10 milliseconds to wake up. Now, bigger, complicated things take more time to wake up because they have more state, whereas lighter weight stuff can go more rapidly in and out of this thing. Again, this data is old, so don't go by the absolute numbers. If I were to look at numbers for now, current stuff, it's the same story. Simple stuff tends to be less efficient in active mode, but more efficient for power management because it can rapidly wake up and go to sleep, and it consumes much less while it is asleep. One of the reasons why power goes up for big things when they're asleep is because they have more transistors, and transistors leak. Even just because they're powered up, they leak certain amount of power. So if I'm looking at a 32-bit processor versus an 8-bit processor, very crudely, 32-bit stuff will at least have 4 times as many transistors. So right there, its sleep power is going to be at least 4 times. In general, it tends to be a lot more. So sort of takeaway from this part really is that there's a big dynamic range of choices of processors available, and the sweet spot tends to be complicated. So since I have 2 minutes, I'm not going to move to another slide, but go ahead. It's the execution energy. So to do one CRC, how much energy it took?
Is it fair to compare, for example, we have to give them the same task. If I want,
it's the same task. So I'm doing CRC over the same packet. So same task, same packet, identical computation. How much energy? Obviously, the 8-bit processor takes more time. During that time, it's consuming less power, in the sense the power level is low, but the product of power times time, which is energy, is a lot higher.
So you are using, in this case, you are using 8-bit processor to process data of length 32-bit, right?
Whatever is the data. I mean, it could be some other number of bits.
The same, right?
Yeah. It's the same data, same algorithm.
So we need like 4 times around.
Well, so firstly, to begin with, so I don't know precisely whether the data was 32-bit or 8-bit, and also in the case of FFT, actually it was floating point, which is a killer because you have to do floating point. Actually, neither one of them had floating point hardware. So in either case, they are doing floating point emulation. It's just that this poor guy is trying to do it with 8-bit hardware. Okay, so a lot more complicated because your floating point natively is many more bits, so you have a lot more shifts and all going on. Just imagine if I have to do 32-bit addition using an 8-bit hardware, it's not simply 4 times, it's actually more than 4 times. Okay, so that's what you're kind of paying for. Okay, is it fair or not? That's what my task needed. Okay, so yes, it is fair.
And then when you say there's a dynamic variation between the microcontrollers, is it only between the number of bits that they process, or is it like even within the 32 bits microprocessors?
Even within 32 bits it is, and even within a single processor it is. We're going to touch upon that because I can change voltage, change frequency. Okay, so processors tend to be much more complicated. Next time around, what we'll see is the following. So a week from now, no class on Monday. It's the following that just like in memories, we create hierarchies of memories, right? We have fast memory and somewhat slower memory and even slower memory, and we create a hierarchy. That's what is beginning to happen in processors also. We combine processors with different characteristics, put them next to each other, and then depending upon my workload, power up one or the other. Okay, and that's the game that we're going to play. And that's what's happening in embedded system. That's how we achieve kind of lower power. And that, by the way, happens not just for processors, it can happen for other things also. So kind of one very interesting example I learned recently was a new iPhone 6 and 6S, whatever, 6, the big 6. It has 2 accelerometers. So one which is a lower power, less accurate, and one which is higher power, more accurate. They use the higher power, more accurate stuff for fine motion detection and all, whereas the lower power one is for your pedometer kind of application, always on and on. Okay, so even for other things, same characteristic. same notion kind of holds true. Okay, so let's stop out here, and we'll see you next week.